So far, we have focused on discrete random variables. The discrete random variables have finite or countably infinite number of possible values. Remember, countably infinite means that the values can be counted using the numerals 1, 2, 3, 4, 5, 6, 7 until infinity. If you can count them, it's countably infinite or finite. Discrete random variables have finite or countably infinite number of possible values, and the distribution of such random variables can be described in a table like this. In a table, you can list all the possible values of the random variable, say x1, x2, x3, to the end of all the values. Or if there is no end, then just keep going. And the probability, and the second column of the table can list the probability that x equals each of these values, say p1, p2, p3, da da da. And all the probabilities should be non-negative, and they should add up to 1. For discrete random variables, to calculate the probability of an event A, we can sum up the probability that x equals each of the values in A. So probability that x belongs to the event A, or PA, equals the sum over little x in A, px equals little x. So that's straightforward enough. But there is an equally important class of random variables that is called continuous random variables. A continuous random variable does not have finite or countably infinite number of possible values. Instead, the number of possible values for a continuous random variable is uncountably infinite. For such variables, we can no longer rely on the probability that x equals little x for x being each of the possible values to describe the distribution of x. We can no longer rely on the probability table to describe the distribution of x. To see why that is the case, let's consider a simple example. Suppose that this circle here represents a spinner. A spinner is just a piece of cardboard on which you have a circle like this. And in the middle of the cardboard, you have a hand like the hand of a clock. So this hand can spin. You can spin this hand. And when you spin it, it might stop at some point, right? So when you start the spinning, after some amount of time, the hand will stop spinning and stop somewhere. So where it stops, let's call where it stops the x random variable. So the circle, the points on the circle are labeled by numbers. So you go from the topmost point and you call that 0, and then you move around the circle evenly, and give each point a number until you reach the topmost point again. And so that point is both 1 and 0. And the bottommost point is 0.5. And the rightmost point is 0.25 and leftmost point is 0.75. Let's suppose that the points on the circle are numbered evenly in this way. Then where the spinner stops, the number corresponding to the location where the spinner stops is the random variable x. So that is the random variable x. As you can see, this random variable x is not a discrete random variable because the spinner could stop anywhere around the circle. And there are an uncountably infinite number of points on this circle. So x could take any value in this uncountably infinite set. In fact, this set of possible values is the interval 0 to 1. And let's see why probability that x equal little x, this kind of probability is not helpful for describing the distribution of x. Suppose that the spinner is a fair spinner, meaning that it doesn't favor any point on the circle. So when you spin it, it could stop at any point with equal probability. So the probability that x equals little x is the same for any x on the circle. Right, so that comes from our assumption that the spinner is a fair spinner. So it's a fair spinner, and that intuitively tells us that the probability that x falls on any point on the circle is the same. Well, that seems informative, but what is this probability P? This probability P, we can show it cannot be a positive number. Suppose the contrary, suppose that P is a positive number. Then we can choose x1, x2, 2xn distinct points. x1, x2, xn are all different numbers. That is, so this is a subset of 0, 1 in different numbers on 0, 1 interval. Then probability that x equals each of these numbers should be P by the definition of P. And that means probability that x belongs to this set should be n times P by axiom 3. The third axiom of probability, right? Because the probability that x equals each of these numbers are disjoint events, and the probability that of the union of this event, which is the event that x belongs to the set of the n points, should be the sum of the probabilities that x equals each of the point, which is P by definition. Therefore, that probability should be NP. But I didn't say what n is. In fact, on this circle, well, or in this 0, 1 interval, you can choose an arbitrarily large n. You can choose an arbitrarily large number of points that are all different from each other. So if P is greater than 0 and the N, there can always be an N large enough such that NP is greater than 1. Well, all you need to do is to choose an N that is greater than 1 over P, which is a positive number. You can always choose an indistinct point like this, such that N is greater than 1 over P, then, so can always let then NP is greater than 1, which is not good news, right? Because NP greater than 1, that means the probability that X is one of these N points is greater than 1. That violates one of the axioms of probability. Violating axioms 1 and 2. So that means, so this implies our premise that this P is positive is wrong. So this X random variable, this continuous random variable, cannot have positive probability at any particular point on the circle. If probability that X equals little x equals 0, which has to be the case according to our derivation here, then this probability is not very useful for describing the distribution of X. Because from these zeros, we cannot figure out the probability that X belongs to any other set, any interval, for example. So for continuous random variables, in general, probability that the random variable equals each point is not useful for describing the distribution of this random variable. Because in general, this probability has to be 0. So what we have described is that P has to be 0. And that is not a very useful description of the distribution of X. Well, instead, we're going to define some other concepts that can be used to describe the distribution of continuous random variables. The first is cumulative distribution function, or CDF. The cumulative distribution function is denoted capital F subscript X, meaning that this is the CDF of the random variable capital X. Capital F sub capital X evaluated at a point little x. This is defined to be probability that X is less than or equal to little x. So that is the definition of the cumulative distribution function. And we can define this cumulative distribution function for the spinor, for the fair spinor example. And we'll see that it contains more information than the probability that X equals little x function. For the spinor example, we know that X could fall on any point in the interval 0 to 1. And because we require this spinor to be a fair spinor, that implies that X should fall on any interval any subinterval of this interval at a rate that's proportional to the length of that interval. So fx of little x should be probability that x belongs to 0 to x, and that should be proportional to the length, which is x. That should be proportional to the length of the interval. So it should be some constant times the length of the interval. But what is the constant? We can figure out the constant using one of the axioms of probability. Axioms of probability tells us that probability that x less than or equal to 1, meaning that x takes any value between 0 and 1. And we know that x can only take value between 0 and 1. Therefore, this probability is the probability of the universal set. So that should be 1 by one of the axioms of probabilities. And this probability should also be x belong to the 0, 1 interval and should be proportional to the length of the interval. So it should be the constant times the length of the interval, which is 1. And this one comes from axioms of probability, and this one comes from what we assumed about the spinor. We assumed the spinor to be fair. Therefore, we want the probability that x belongs to any interval to be proportional to the length. Okay. So these two are equal, and that suggests C has to be 1. And therefore, the CDF of the x random variable should be just x. For x belong to 0 and 1. In fact, for CDFs, we often define the CDF not only on the support of the random variable, but also on the whole real line. So we complete the function in the following way. So what should be the probability that x is less than or equal to a negative number? Well, because x cannot take any value that is negative, therefore that probability should be 0. And that's consistent with the definition of CDF. And what about the probability that x takes a value less than or equal to a number that's greater than 1? Well, because x always take value that is less than 1, and therefore less than a number greater than 1. So the probability of x less than or equal to little x for x greater than 1 should be 1. And this completion is also consistent with the definition of the CDF. So usually we write the CDF as a function that maps from the whole real line to the 0, 1 interval. So this is the complete representation of the cumulative distribution function of this x random variable in the fair spinor example. The cumulative distribution function can be used to calculate probabilities of other events. For example, given this CDF, we can calculate the probability that x belongs to some interval. How do we do that? We should recognize that x belongs to this interval this interval A, B, A to B, so half open, half closed interval. This interval union minus infinity A equals the interval minus infinity B. So we recognize that this is true. So how do we recognize that? It's quite simple. You can draw a real line, and here you have A, and here you have B, and this is the interval A, B, and this is the interval minus infinity to A. So clearly the union of the two is the interval minus infinity to B. And also it's clear that from the picture that these two sets are disjoint. Therefore, probability that x belongs to minus infinity b, which is the union, equals the probability that x belongs to a b interval plus probability that x belongs to minus infinity a interval. So this is by axiom 3 of probabilities, the third axiom of probabilities. So therefore, this probability equals, so this probability right here equals, so that probability is this part. So that equals the probability of x belongs to the minus infinity to b interval minus probability that x belongs to minus infinity to a interval. I should apologize, this all should be capital X, not lowercase x. So that should be probability that x is less than or equal to b minus probability that x less than or equal to a. And by the definition of cumulative distribution function, this is the cumulative distribution function evaluated at B minus CDF evaluated at A. So this is how you use CDF to calculate the probability of other events. And in the continuous random variable case, the other events are usually stated as intervals. Cumulative distribution function is useful for describing the distribution of continuous random variables, but it should also be understood that it's not unique for continuous random variables. It can also be used for discrete random variables. Let's consider some of the discrete distribution that we have discussed so far. For example, the Bernoulli P distribution. If x is Bernoulli P, then x could take two values, 0 and 1. The probability that x takes the value 0 is 1 minus p. Probability that x takes the value 1 is p. And based on this distribution, which is also called the probability mass function, we can figure out the cumulative distribution function. So the CDF at x equals 0 is the probability that x is less than or equal to 0. Well, there is only one value of x that can be less than or equal to 0, which is 0. Therefore, that probability equals the probability that x equals 0. So that should be 1 minus p. And what's the probability that x is less than or equal to 1? Well, that should be 1 because all the possible values of x are less than or equal to 1. So when you calculate the CDF, you simply take the cumulative sums of the column that describes the distribution of the discrete random variable. When you draw the CDF of the Bernoulli random variable on the graph, on a two-dimensional graph, say on the horizontal graph, horizontal axis, you have x, and vertical axis, you want to draw the CDF. Then this CDF value equals 1 minus p when x equals 0, as you can see here. And the CDF equals 1 at 1 when x equals 1. What about, well, as we just have talked about, we usually define CDF as a function that maps the whole real line, not only the support point of the x random variable to 0, 1. So we need to also complete the CDF function for the other points. For the other points on the real line. So for little x that are less than 0, it's clear that there is no probability, 0 probability that the Bernoulli random variable can be less than that negative number. Therefore, the CDF on this portion should be 0. Until you hit the point 0. Once you hit the point 0, CDF jumps to 1 minus p. And for the points between 0 and 1, the probability that the random variable is less than a point between 0 and 1 is equal to the probability that the random variable equals 0, because that's the only value in that range that the random variable can take. Therefore, this CDF stays flat on this interval until you arrive at the point 1, the other support point of the random variable. When you arrive at the point 1, the CDF function jumps to the value of the CDF function at that point, which is 1. And when you and for the x values that are greater than 1, it's not possible for the CDF to grow any further, so the CDF will stay constant, stay flat. So the CDF for the Bernoulli random variable looks like a steps. It's a step function with 2 jumps, 1 at each of the support points. We can do the same thing, calculate the CDF for the Poisson random variable. Let's say the Poisson 1 random variable. The distribution of the Poisson 1 can be described by this column. If we use the Poisson formula to calculate, these are the probabilities that we get for the x values that are 0, 1, 2, 3, da, da, da. And to calculate the cumulative distribution function, we just do a cumulative summation of the numbers on this column. The CDF at the point 0 is 0.37. And to get the CDF at the point 1, we sum up these 2 numbers. So we do a cumulative summation. We sum up these 2 numbers, we get about 0.74. And to get the CDF at the point 2, we sum up these 3 numbers. The sum of these 3 numbers is about 0.92. And to get the probability, to get the CDF that at the point 3, we sum up these three numbers, sorry, these four numbers that come before or at 3. And that give us 0.98. So that's 0.92 plus this extra probability, 0.06. So you get 0.98. And you can keep going and get more points. And when you draw the CDF on the graph, you do the same thing. You first draw the CDF, the value of the CDF at each of the support points, and then you complete the graph by these horizontal line segments. And that is the CDF of the Poisson 1 random variable. So here is some features of CDF for discrete random variables. CDFs for discrete random variables are step functions. They are step functions, that means that they are flat, except that there are some jumps, vertical jumps. And the jumps, where do the jumps occur? Jumps occur at support points of the random variable, and the size, how much the jump is, how much it jumps, the size of the jump at a support point little x is equal to probability that x equals little x. So these are the features of the CDF for discrete random variables. CDFs for continuous random variables do not have jumps. And in fact, CDF for continuous random variables are continuous. For continuous random variables, we can define another function that also describes its distribution, which is the probability density function, or PDF. The probability density function describes how likely X falls in the vicinity of each X. Well, we already know that for continuous random variables, the probability that X falls exactly on X is 0. But the probability of X falls in the vicinity or in a small neighborhood around X is not 0. And how likely it is to fall in the vicinity of each X is described by the probability density function. So what is the probability density function? When the CDF is continuous, meaning that we are dealing with a continuous random variable, when the CDF is continuous and differentiable except on a finite number of points, it doesn't have to be differentiable everywhere. It can be non-differentiable at some point, but only a finite number of points. Suppose that fx satisfies this, then we can define the probability density function to be the first derivative of the CDF function. Well, you might wonder, when it is differentiable, this derivative exists, you can define the PDF at that point to be the derivative. What about the non-differentiable points? It turns out that at the non-differentiable points, it doesn't matter what value you give the PDF. It will not affect any calculation that you do using the PDF. Usually we give value that makes the PDF function also continuous. So that's the definition of probability density function. And conversely, we also have the following relationship. The CDF is the integral of the PDF. Not any integral, but the integral from infinity to little x of the PDF. So we have these two relationship of the PDF and the CDF. Now let's consider the fair spinner example again. For that example, we have calculated that the CDF is this. The CDF is 0 for x that are negative and equals x for x in the interval 0, 1 and 1 for x greater than or equal to 1. When you draw that CDF on the graph, you find that this CDF is 0 on this negative portion, and it's the 45-degree line on the 0 to 1 portion, and flat at 1 when x is greater than 1. So that is the CDF for the random variable x, that is the location, the outcome of the fair spinner. As you can see, this CDF is continuous, and it's also differentiable except at only 2 points. So we can calculate the probability density function by taking the derivative of this function. So the PDF is the derivative of the CDF. The derivative is only non-zero in this portion, and in this portion, the derivative is 1 for x belong to 0 to 1 and 0 otherwise. Notice that at 0 and at 1, the CDF is not differentiable. So you can use closed interval or use open interval. It does not matter. So it does not matter what value you assign the PDF at the non-differentiable points of the CDF. So here I'm assigning 1 to the PDF function at these two non-differentiable points of the CDF. But you can do the opposite. You can assign the value 0 to these points as well. And the PDF can be drawn on the graph as well. So this second graph describes the PDF. So this is the horizontal axis is x, vertical is the PDF, probability density function of x. That function is 0 outside the 0, 1 interval and is flat at 1 on that interval. So that is the PDF. And we can find event probabilities using the probability density function. Remember that we have used the CDF to find the probability that x belongs to this interval a to b. We can do the same thing using the PDF. So this probability we have found, it should be the CDF at b minus the CDF at a. And the CDF evaluated at b is integral minus infinity to b fx little x minus integral from minus infinity to a, this PDF dx. And the integral, by the definition of integrals, so suppose this is a PDF. So that is, suppose that is the PDF. Suppose that is your little f(x), and it's 0 otherwise. Suppose that is the PDF. Then the integral of that on the interval minus infinity to b is the area under this PDF function, just by the definition of integrals. And similarly, the integral on the interval minus infinity to a, so that's a, is the area under the PDF on that interval. So the difference of the two areas will be, clearly will be the area that's here, the area under the PDF should be the area under the PDF in the interval a to b. So that clearly should be from a to b fx little x dx. So that's how you can obtain event probability using probability density function. And you have to be a little careful here. Suppose that little a is not here, is not in the support of the random variable. Suppose a is somewhere here. So suppose this is b, but this is a. Then the probability that x belongs to a to b interval is still the integral of the PDF on this a to b interval. But on this a to b interval, part of it, part of the PDF is 0. Only the other part is non-zero. So you can write that, in this case, you can write that as you should, sorry, when you calculate that integral from a to b, you should be aware of this discontinuity here. Okay, this formula is still correct, but you should be aware of what formula to use on what interval for the PDF. So the probability density function is a density. A final word that I want to say about this is that is what the density, the word density mean in probability density function. So density can be understood in the following way. Suppose you are throwing points on the real line, and where the point falls, suppose where the point falls is the random variable x, and it follows the distribution described by the probability density function. And when you throw many, many points according to this distribution on the real line, then where the points are very dense is where the probability density function is high. And where the points are not dense is where the probability density function is low. So that's intuitively what density means in the probability density function.